to an associahedron. This is something coming from Noncrossing sets, and after we submitted it to the FPSAC, we put it on the archive, and then some days later, David Spire told us that some of the results were already known, some of the important results in there, and then a few weeks later, he sent us another email and saying, oh, I found yet another paper that already contained the definition somehow. So I'm basically telling you a story about things that were known for a while, but I guess most of you have not seen it before. Okay. Maybe start about the setup. We want to study a binary, so-called non-crossing relation on K subsets of an n-element set. And if K is equal to 2, this should be the usual non-crossing condition on arcs, which I can draw. If I draw big, you might see something. So we don't want, if K is equal to 2, to see two crossing arcs. But now the question is, what is the right definition of a non-crossing relation if we consider K subsets? And then we want to study the simplicial complex of pairwise non-crossing collections. So collection, we take collections of K subsets that they are mutually non-crossing. And why do we want to study these? We want to generalize the simplicial complex of triangulations, as I just said, and we want to generalize some of its algebraic properties, some of its geometric properties, and some of its combinatorial properties. So the original motivation was that we want to understand the Hilbert series of the Grassmannian, and we want to find a simplicial complex for which the Sandler-Reisner ideal gives us a really nice monomial ideal for the defining ideal of the Grassmannian. This is just an algebraic property, and this is something we hadn't seen before. And if you want to phrase it in terms of geometry, this is saying that we want a simplicial complex that is a particularly nice triangulation of an order polytope of a square grid, of a rectangular grid. This square should be rectangular. And as such, should generalize the associahedron. So for K equal to 2, this 2 by n minus 2 grid, if you take the order polytope, then the associahedron, one way of seeing the associahedron is a triangulation of this polytope. And finally, the third property is the combinatorial property, which is saying that we want for K equal to 2 again, we have a natural ordering on the dual graph of the complex of triangulations. By the dual graph, I mean a graph on the facets of the simplicial complex, the vertices, and the edges are facets that share a codimension 1 face. So we want an orientation on this graph that generalizes the Tamari order for K equal to 2. So again, if you want to draw a picture that you might be able to see. So this is how for K equal to 2 and n equal to 5, we have the 5 triangulations as the vertices of this dual graph, and then there's an orientation of the edges, and this is then the associahedron. And we also want to study for higher K, we want to understand an orientation that yields generalized Tamari order. Okay, after the setup, what is the non-crossing relation? And it's actually a very, very simple definition. Namely, if we start and we want to consider 2 of these K subsets of n, and we say these guys are non-crossing if basically if we take 2 indices A and B, then we want that the arcs IA, IB and JA, JB do not cross. And we want that not for all pairs of A and B, but for only those pairs for which the sequences A and J, I and J coincide in between. So this is basically saying we only want that for consecutive pairs, except that we first remove all the coincidences in a given position in I and J. So the example would be, here we have K is equal to 5 and N is equal to 9. Then we look at these two sequences and we check if these guys are, if it's crossing or non-crossing. So what we do is we write the numbers 1 through, can actually everyone see if I write big? So the first check we do is, oh, I skipped the 7. That's okay.
It's very hard to see the board.
Yeah.
Still?
It is. And there's a light.
It's the lighting.
Oh. It's the bottom box.
No.
It's a bit better.
Is it better? Okay.
It's better.
So,
That
so the
was
first test we want to do is we test the arc 1,4 and the arc 2,3. And as it's not too hard to observe that these two guys are non-crossing. So I'm testing the next arc. So we have the 4 and the 8 and the 3 and the 7 because the 6 coincide, so we remove these guys. So we have a 4 and a, what was that? A 4 and an 8 and a 3 and a 7. And these guys cross here. That turns these two K subsets into crossing subsets. But if I replace the 6 by a 5 in the first of the two, then this becomes non-crossing because I'm not testing these two pairs anymore, these two arcs anymore, because now we have the guy in the middle doesn't coincide. So now I'm testing 4, 5 and 3, 6, which is non-crossing, and 5, 8, 6, 7, which is non-crossing. So this should really say this is a local condition and it's not about all arcs, but you really have to restrict to some of the arcs. I guess the definition should be clear to most of you, so I keep going. The non-crossing complex is then just the simplicial complex where the vertices are such K subsets and the faces are collections of non-crossing K subsets. And by construction, basically, if you plug in K equal to 2, this is just the usual complex of triangulations of a convex polygon. And a well-known fact is that also for K subsets, a notion of non-nesting already exists. And this is just, we take for any two indices, A and B, we want that the arcs do not nest. So the definition of non-crossing is a little more restrictive in which arcs I'm actually testing. But it turns out I don't need to test all of them here. It would be enough to actually test the same as up here to get the same notion of non-nestingness. So the definition looks a little more restricting up here, but it's just the same thing. Simply because nesting is transitive while crossing is not transitive. This complex, purely combinatorially defined, has many very simple symmetries. Namely, if I send A to n plus 1 minus A, it induces an automorphism on this simplicial complex, which is basically saying I'm just flipping this picture in the middle. The second says that if I have two K subsets, then they do not cross if and only if their complements do not cross. They're complementary n minus K subsets. So that induces then an isomorphism between these simplicial complexes. Then, if two guys cross, that only depends on their symmetric difference. So, by definition, I'm only allowed to ignore guys that coincide at the same position. But it's not too hard to observe that it's actually enough if you, in general, restrict to the symmetric difference. Then you can project down in dimension, either if I have an element which is in a given facet of the complex, then I'm getting, and then I'm projecting down, then I'm getting the simplicial complex of parameters k minus 1 and n minus 1, or if it's not in there, then I'm getting the complex of parameters k and n minus 1. So this could give a way of like recursively construct the complex, but we didn't really see any advantage of doing it this way. And then we have that if I take the vertex 1 through k and rotate it cyclically around the outer circle, then these are non-crossing with any other vertex. Simply because in the definition of the non-crossing, I need some space between two entries here to actually make something crossing. And last but certainly not least, this complex is not symmetric by rotation of the outer polygon. So if I have a triangulation of a polygon, something like this, then if I rotate, I'm getting again a triangulation. So for k equal to 2, this complex is symmetric under rotation. But for higher k, the complex we gave is not symmetric under rotation, which is a little annoying. But the problem is, if we want the properties we are desired which we desire from the complex, it is actually impossible to make it rotationally invariant. Simply because it's a flat complex and I don't have enough. I mean, if I look at orbits under crossing pairs, I'm not getting the right number of orbits, so I can't get the right edge. I can't get a complex having the right edge vector to have these two properties. So we can't get away with this.
So it's not possible to come up with a cylindrical definition?
Pardon?
It's not possible to come up with a cylindrical definition of non-crossing?
Of course you can come up with one, but it's not going to have these properties.
You mean the other property?
Yes, you can't. I mean, this then can't be a nice triangulation of this order polytope, and it can't have the H vector of the Grassmannian.
Could have other interesting properties.
I didn't go for it. Okay, so a few words on how to identify this complex with the order polytope. This is just, I mean, the order polytope for any poset. One way of saying, defining what it is, it's the convex hull of the characteristic polynomials of the order filters in the poset. So if I'm here, if this is my poset, so it's a grid poset 3 by 4, and I'm taking an order filter in there, then this is then just the sum of the coordinates 1, 3, 1, 4, 2, 4, 2, 3, 3, 2, 3, 3, and 3, 4. And if I take that for every order ideal, I'm getting, if I'm doing that for every order filter, I'm getting the order polytope. It's the convex hull of all of these. So the two trivial examples are, if I have an anti-chain, there is no relation, any subset is an order filter. So I'm getting the complete cube because I get all 0, 1 vectors as vertices. And if it's a chain, then I'm only having as vertices, I'm having the 0 vector, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, so I'm getting a simplex. These are the two extremal examples. And how to get from our case subset that we have looked so far at to the order filters is just by, I start with an order filter, I draw such a path in the dual grid, and record the positions of the down steps. So this order filter on the left corresponds to this, the 3 subset of 7, it's 2, 4, 5. So it's a very simple way of identifying k subsets of n and order filters in the k by n minus k grid. Okay, and then the theorem, which in slightly different words, and some of the terms were only conjectured, though their methods already contained the proofs, is that this complex is actually an S-nice triangulation of the order polytope as we wanted it from the beginning on. And the first corollary, not really of this theorem, but of the properties, of this last property is that I have a complete simplex which I can take out of the construction, because these are non-crossing with anyone and there are n of them. So I'm getting a decomposition of this simplicial complex into an n-1 dimensional simplex, and then a flat polytopal sphere of the complementary dimension. And this complex has all the desired properties from the beginning. The first corollary, or another corollary that we shortly look at is this is that as it's a triangulation of a polytope, it's pure, and since we can predict the h vector of it, we see that the number of facets is exactly this multidimensional Catalan number, which is the number of standard Young tableau of the shape n minus k to the power k, which is exactly this shape. So the number of standard Young tableaus of this shape, so but where the vertices, you label the vertices with the numbers, is exactly the number of facets of our complex. And one open problem, if anyone want to look at that, is we don't know any explicit bijection between the facets of our complex and standard Young tableau of shape k by n minus k. And the h vector is given by the multidimensional Ariana numbers, which has a more or less explicit expression, but that's huge, so I'm just telling you how you can construct it. It's the number of standard Young tableau of this particular shape having I peaks. And the peak in the tableau is just an entry I somewhere, such that I plus 1 is in a row below I. Or above I? It's the other way around. I and I plus 1. So, sorry. So, a position A is a peak if A plus 1 is placed in a row lower than A. Okay, let me think for a second. Okay, the point is I'm actually ordering my standard tableaus from here. That's why. So this is going to be the 1 in my tableau. And this is going to be the k by n minus k. So it's sort of the number of descents of the standard tableau. And so what's wrong?
Why isn't it a descent?
You can, I don't know, people called it, in the literature we looked at it, they called it a peak and not a descent. You can call it a descent. That's okay. So
Peak in standard school.
It's called descent in the literature.
Maybe again I would ask for such comments to delay until the coffee or as soon as a ring can be organised.
thank you so much. Okay, so not only we are in the end we are not only looking at facets and want to connect them to standard Young tableau, but we also want to have the refinement of the h vector being related to standard Young tableau with I peaks or descents. After we have set up and stated the main theorem there, and we want to go a little into the combinatorics of the objects, because there are still a lot of open problems, which I hope that some of you might be interested in. So if we start with a multi-set of such k subsets, then we arrange them into columns of a table ordered lexicographically. So here this is the vector, or the k tuple 1, 2, 3, 1, 2, 4, 1, 3, 5, 2, 3, 5, 2, 4, 5, and so on. Okay? So if I have a multi-set of such k subsets, I arrange them in a table. And then I record the entries. And the 3 just says I have 3 1s. The 7 says I have 7 1s and 2s. The 8 says I have 8 1s, 2s, and 3s. This 8 says I have 8 1, 2, 3s, and 4s. And the 5 I don't really need to record because that's the highest number. So this is always going to be the number of vectors I have recorded in total. The same here. I have this 2 is this 2 number of 2s, the 4 is the 2s and the 3s, the 6 is 2s, 3s, and 4s, and so on. And one observation is that what we see on the right is a weakly increasing tableau, again starting from the bottom left. And it's weakly increasing in both directions. And that these tableaux are exactly encoding the lattice points in the cone over the order polytope. And the reason for that is the order polytope, remember, it's the convex hull of the order filters. So a lattice point in the cone is just a weighted sum of order filters. But an order filter is just an upper part in this piece here. So if I take a weighted sum of them, I'm getting exactly all tableaux that are weakly increasing along rows and columns, starting from the bottom left. And the combinatorial main theorem of the construction is that if I start with any such tableau, then I can construct a unique multiset of mutually non-nesting vectors and a unique multiset of mutually non-crossing vectors. Except that I have to remove this trivial k subset, and the reason for that is this is not contributing at all to the recording tableau. this case subset under the bijection down here corresponds to the 0 in this column. That's why I have to remove it. So, and given this combinatorially implies directly that this symplectic complex, that the non-crossing and the non-nesting symplectic complexes both triangulate this order polytope. Because that's one way of describing a triangulation of a polytope, by saying that if the one vertex is the 0, that every point in the cone has unique decomposition into faces of the triangulation. And since I have some minutes, I can give you a quick idea of how we start with such a tableau, and we want to construct these two sets of mutually non-nesting and mutually non-crossing vectors. And what we do is, so the entries in the tableau tell us how often a certain number appears. So this 3 says there are 3 ones in the first row. So the first row is just, we write from left to right the numbers according to the first row here. So I'm writing 1, 1, 1, 2, 2, 2, 2, 3, and that's it. And then I have 2 different rules for the non-nesting and the non-crossing situation. And then for the non-nesting is, I'm inserting a number, and I'm always inserting it into the reflex smallest possible position. So imagine I've written down here, when I insert which, I insert where, and what I just said is just another way of saying I'm just writing them from left to right for the non-nesting triangulation. But this is nothing new. The idea is more important for the non-crossing triangulation, where I'm now not taking the reflex first, but the reflex last position in which I can put this guy. So imagine I have put the both 2's here in the reflex last possible positions, which are, it's just a piece up here, so that's just the 2 1's. Now I want to insert the 3's. Then I'm looking for the reflex largest position in which I can insert a 3. This is the 2. So I'm not inserting it above the 1 because the 1 is reflex smaller than the 2, reading from bottom to top. And just by this construction, it is not too hard to see that this is the only way of filling the complete table, such that I'm not creating crossings in this situation and not creating nestings in this situation. So it's not too important that you really see how the procedure is. I'm basically only saying there is a unique way of proceeding to get these 2 tables. And the marks in there are, I just mark for every entry, I'm marking the last guy I've inserted into the table. So for example, here in this table I've inserted 2 4's. I've inserted this first, so this 5 in the corner says I inserted this as the 5th letter, and this I've inserted as the 6th letter. So I mark this 4. So all that's saying is I'm inserting the numbers 1 by 1, and the last occurrence of each number I just mark somehow. This just gives me some information about how I encoded this non-crossing and non-nesting tables. And then once you have set this up, this construction, you can stare at it for a while, and then you can figure out that these 2 collections of non-crossing and non-nesting sets are facets of the corresponding complexes, if and only if every column contains a unique mark. In particular, these are both not facets, because this column contains 2 marks, this column contains 2 marks. And these 2 tables or collections of case subsets are a codimension 1 phase of the complexes if and only if every column contains a unique mark except for one which contains then 2 marks. And this is just another way of saying, this is going to come on the next slide, that every codimension 1 phase is, by this combinatorial game, forced to be in exactly 2 facets of the complex. So that's saying this is a pseudomanifold. I mean, we know that already that it's a polytope, but this is, we use some little more heavy machinery than just a very simple combinatorial game to play. And finally, when we have a table where that is not mutually non-crossing or non-nesting case subsets, I can always take a marked entry in a column that contains more than 1, and there is a pushing procedure. Which is, for example, I'm taking this 4 and then I'm pushing this 4, whatever that means, and it just creates a new vector which is non-nesting, respectively non-crossing with all the others. So this is like a procedure of getting from a lower dimensional phase of the complex towards the top dimensional phase. So this is then, and as corollaries we get that of the combinatorial, simple combinatorial observation is that both complexes are pure of the dimension we desire, and that every codimension 1 phase is contained in exactly 2 maximal phases. And having set up this pushing procedure, it's not really necessary to really know how it exactly works, but just it's a very simple combinatorial game to play. That then yields orientation of the dual graph. And the dual graph of any complex or any pure complex we want to define as the graph with vertices being facets of the complex and with undirected edges being pairs of facets that share a codimension 1 phase. And then one can see that this pushing procedure, so I'm sitting in I want to orient a codimension 1 phase basically. So the question is in which order do I put them? And the idea is if I have a codimension 1 phase, there is exactly 1 column containing 2 marks. Then if I'm pushing the top of the 2 marks, I'm going down, and if I'm pushing the bottom of the 2 guys, I'm going up. Or the other way around, it doesn't really matter, just you have to fix one of them. So that gives a very simple way of orienting the dual graph of this non-crossing complex. And this is the Grassmann-Tamari digraph. The problem is at that point it's totally unclear that this is going to define something acyclic. So you have to do some geometric work in order to prove that this is actually an acyclic graph, so we can study its transitive closure. And from the procedure I briefly mentioned, we get 2 symmetries. The first is that this Grassmann-Tamari order is self-dual, and the map is explicitly given, and the 2 Grassmann-Tamari orders for parameters kn and n minus kn are isomorphic. And that's basically all we know about that complex. So now you can quickly, here's a picture actually. This is the situation k equal to 2 that you all know, and here's the dual situation for k equal to 3, which is 5 minus 2. So, and to close, I want to pose the conjecture that this is always a lattice. So far we have really no idea why this is the case, we can't compute too much, but the first examples indicate that this might be the case. And the second corresponds to this observation that we have seen these numbers that are the number of standard Young tableau having I peaks slash descents, and this is exactly equal to the number of facets in my simple division complex which have I upper covers in the Grassmann-Tamari order. So the question is, what do we do with this equality? On the left hand we see something on standard Young tableau, on the right we see something on this Grassmann-Tamari order, and the question is there a way to define this Grassmann-Tamari order we have seen here on the right directly on standard Young tableau? So which is basically saying to take a standard Young tableau and a peak, and from this data you create a new standard Young tableau, which is for DIT paths. For a DIT path and a valley in the DIT path, you create a new DIT path by the Tamari shift, but for general K. And here, if we had such a bijection, you would then also find this would induce a bijection between the facets of the non-nesting complex and the facets of the non-crossing complex. Or in other words, it would give a bijection between the facets of the non-crossing complex and standard Young tableau. And of course, we want that this order should be generalizing the ordinary Tamari order on DIT path. And that's all. Thank you.
So at the risk of eating into lunchtime ever so slightly, are there any questions for Christian Stump?
So if I really do care about cyclic symmetry, is there a way to modify your construction to get something that's cyclically symmetric? If I could care less about those other properties? you can assume that.
I don't really know how to do that. The point is, if we want in the very beginning, so this is what we are aiming for, such a construction, such a complex, then we just get the H vector predicted.
Okay.
And if I take pairs of 3 subsets of where n is 6, yeah,
Yeah.
then one such pair is either crossing or non-crossing. But if you want something that's cyclically symmetric, I'm getting orbits of such pairs. And just the number of orbits, the number of elements by units of orbits is not going to give you the right number of edges I have to get this complex.
Okay.
So for this construction, as soon as you want these algebraic geometric properties, you have no chance. But that's not saying you can't come up with any construction.
And
Just
have
not
you
for
thought
these
about
two
that,
properties.
Like sort of throwing some of this away, but you want them to be cyclically symmetric, or?
So what you can actually do is you could now study the cyclically symmetric part of this complex.
Okay.
And this is actually the complex of weakly separable sets from Zelevinsky and co-authors. I currently don't remember who that was. So, pardon?
Leclerc and
Oh, Leclerc and Zelevinsky, thank you. So if you take the cyclic part of this complex, this is exactly the weakly separable complex of Leclerc and Zelevinsky studying quantum cluster algebras.
Okay.
So if you want to study cyclic symmetry, it's better go to that complex.
Maybe we'll leave that until. Why not? We're all well fed at this point, so very quick.
It's a yes/no question. So
Even better.
your simplicial complex, you say it's the that there's a polytope, right? That it's a triangulation of. If you look at the dual polytope, then your graph is going to be the one skeleton.
That's right.
Now, and if you take your orientation of this graph, is it induced by a cost vector?
By what?
A cost vector? Could you find a vector?
Oh, yes.
Okay.
I do believe so.
Okay. Good. Thanks.
Okay, well, let's thank the speaker again.